Welcome to the third lesson on combinatorics. In this lesson, I'm going to talk about the labeling principle. I'll do a few examples first, leading up to a general statement of the labeling principle. Then I'll give you a few more examples or problems related to that afterwards. So let's start off simple. We saw this type of problem already in the very first lesson where I quickly went over permutations and combinations. And I want to kind of have a more general rule here in this lesson. So we'll start with distinguishable objects. Consider a set of three distinguishable objects. Objects that are named or labeled in some way so they can be distinguished. The objects can be anything: billiard balls, marbles, people. The labeling can vary significantly. Different shapes, different colors, different names. Basically any scheme that allows one to distinguish one object from another. For the sake of argument and simplicity, we'll just use letters in this lesson. We'll take a simple example here. How many ways can A, B, and C be arranged? For only three objects, it's pretty easy. We can just list them all here. We take A first, and we do B, C, and then CB. And then we take B next as being the first. And then we take A, C, and CA, and then we take C first, and then we have either AB or BA following it. So we can use a similar pattern if we have four distinguishable objects, A, B, C, and D. We use the same kind of idea. If D comes first, then we know from our analysis of three objects that there's six ways of arranging the A, B, or C, and if C comes first, then there's six ways of arranging A, B, and D. If B comes first, there's six ways of arranging the other letters, and if A comes first, there's six ways of arranging the other letters. So it's 4 times 6, 24 ways to arrange four distinguishable objects. For 5 distinguishable objects, we use the same logic as we did for 3 and 4. We take any one of the 5 objects going first, and then we know that there's 24 arrangements for the other 4. So it's just a matter of multiplying 5 times 24 to get 120. And if we recognize 24 as being 4 times 3 times 2 times 1, we can rewrite the answer as 5 factorial. And in general, if we use this logic recursively, we have that the number of arrangements for n distinguishable objects is given by n factorial, n times n minus 1, all the way down to 3 times 2 times 1. So on the next slide, we're going to look at arrangements of combinations of indistinguishable and distinguishable objects. That gets a little bit more complicated, and we'll look at that. And then we'll eventually come up with a general labeling theorem following the example in the next slide. So let's look at the case where we have indistinguishable objects. If we just have, let me point here, if we just have 5 A's, that's not interesting at all. There's only one arrangement there. What becomes a bit more interesting is if we have a mixture. So here you see we have A, B, and then 3 C's and a D. So the C's are indistinguishable. And of course, the A, B, and D are different, and they're from each other as well as they're different from the C's. So it would be wrong to use our formula from the previous slides and just say that the number of arrangements is 6 factorial, because we're going to count things over multiple times because the C's are identical. So one approach is to do the following. Pretend the C's are distinct. So we'll call them C1, C sub 2, C sub 3. And in that case, we do have 6 factorial arrangements of these 6 different objects. Then what we need to do is correct for the overcounting. Since the C's are identical, swapping them around doesn't change the look of a particular arrangement. So look at the example below. If we fix A, B, and D, is shown here, the C's, the distinct C's have 3 factorial different combinations. So here we have C1, 2, 3, then 1, 3, 2, 2, 1, 3, and so forth. So in the real problem, all 6 of these, when I say the real problem, I mean where the C's are distinguishable, all 6 of these appear the same as A, B, D, C, C. Because there are 3 factorial ways to arrange the C's amongst themselves in any particular fixed arrangement for the A, B, and D, our initial calculations of 6 factorial counts every unique partition 3 factorial times. So to calculate the true number of unique arrangements, we need to divide the total factorial, 6 factorial, by the number of repetitions of the C's. And so we get 6 factorial divided by 3 factorial is the solution to our problem. So what I want to do on the next slide is generalize this approach when you have any mixture of distinguishable and indistinguishable objects. Next, consider the more complex example with several repeated labels. So 4 A's, 3 B's, 2 C's, and 1 D. We want to know how many ways of rearranging these objects. So we use the same logic as before, but we need to divide the total possible number of arrangements, 10 factorial, there's 10 objects here, by the number of arrangements lost because of the replicated terms. So we need to divide by 4 factorial for the A's, 3 factorial for the B's, 2 factorial for the 2 C's. And then we don't really need to do this, but just to have nice bookkeeping, we'll divide 1 factorial for the D. That's not repeated, it's just one distinguishable object. So notice that the sum of the numbers in the denominator equals the numerator, ignoring the factorial sign. So 4 plus 3 plus 2 plus 1 is 10. And so we can generalize this to what I call the labeling principle. Given n objects where A sub 1 of the objects have label 1, A sub 2 of the objects have label 2, and so forth, and A sub r of the objects have label r, then the total number of distinguishable arrangements is n factorial divided by A1 factorial times A2 factorial dot 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 times A sub r factorial, where the as I mentioned with this example here, the A sub 1, A sub 2, all the way up to A sub r, they add up to n. And you notice if we had all distinguishable objects where A1, A2, up to A sub r all equaled 1, then you just have 1 in the denominator, and you'd have this solution of n factorial, which is what we had done in the case of distinguishable objects. The ideas in the previous section concerning the labeling principle were developed by James Tanton in his book Thinking Mathematics Volume 2. I don't know if he originated the ideas, but he certainly developed them, and he put forward this approach in a number of videos also. The main idea is to basically eliminate the distinction between permutations and combinations. In my opinion, Tanton is a great educator and expositor of math. I would recommend his book, Thinking Mathematics, Volume 1 and 2, and also his webpage, which points to a number of videos that he's put together and some other information that he is offering to his viewers. So let's look at an example of our labeling principle. We're given n distinguishable items. How many ways are there to select k of the items, and by implication, not select n minus k of the items? So I'll give you the solution on this slide, and if you want to try it, I would pause now, and then I'll come back in a second and show you the solution. So here's our solution using the labeling principle. K items are labeled as selected, and n minus k items are labeled as not selected. Then the total is given by our formula from the labeling principle. So it's the total number in the numerator, n factorial. And then we need to divide out the number of arrangements of the selected, the items that are labeled as selected, and that's k factorial, and then multiply that times the number of arrangements of the items that are not selected, that's n minus k factorial, and you get this here, which is often written in this notation, n choose k. Okay, so let's look at some more examples. I have a few examples on this slide. I'll request that you pause the video if you want to try these, and then I'll give you the solution on the same slide, just as a warning. So let's look at the first one here. Given a container was 10 lottery tickets, how many different ways can a first, second, and third place winner be drawn? Okay, so you want to pause here, and then I'll come back and give you the solution using the labeling principle. Okay, so here's our answer. Using the labeling principle, one ticket is labeled as first, one ticket is labeled as second, we label the other ticket as third, and then 7 tickets are labeled as not winners. So we have a total of 10 that goes in the numerator, and then we have 1 factorial times 1 factorial times 1 factorial for the first, second, and third place tickets, and then we have 7 factorial for the not winners. So when we divide 7 factorial into 10 factorial, we just get 8 times 9 times 10, which is 720. All right, I have another example on the same slide, and I'll give you the answer on this same slide, so you want to pause once I go through this. Given a box with 100 different books, how many different ways are there to distribute 60 books to school 1 and 40 books to school number 2? Okay, so you may want to pause here, and then I'm going to come back in a second and give you the answer. So you may have guessed this one. This was similar to the example from the previous slide. The books destined for school number 1 are given the label 1, and the books destined for school 2 are given the label 2. And then from the labeling principle, we have the total number of arrangements, 100 factorial, and then we need to divide by the number of arrangements of the for school 1 and for school 2, so that's 60 factorial times 40 factorial, which is a very big number, so I didn't bother to list it out explicitly, but this is the answer in terms of factorials. Okay, I have yet more examples, so let's continue. Example number 4. Given 36 school children, how many ways can they be assigned to 3 softball teams, 12 on each team, with 1 captain for team 1, 1 captain for team 2, and 2 captains for team 3? I'll give you the solution on this slide, so if you want to try it, pause now, and I'll come back in a second and give you the answer. So again, this is a labeling, or at least it can be solved using the labeling principle. So 11 children labeled as team 1, and 1 child labeled as team captain, so that makes 12. And then we label 11 children as team 2, with 1 child labeled as the team captain number 2. And then for the third team, we have 10 children labeled as team 3, with 2 children labeled as captain team number 3. So 36 is in the numerator, and then in the denominator we have 11 factorial times 1 factorial for the first team, and then 11 factorial times 1 factorial for the second team, and then 10 factorial times 2 factorial for the 13. And again, this is a really big number, so I'll just give you the solution expressed as the quotient of factorials. This problem and the next problem involve both the product rule and the labeling principle. So consider a deck of playing cards, 13 cards of each suit, clubs, spades, hearts, and diamonds. How many ways are there to select 5 clubs, 6 spades, 7 hearts, and 8 diamonds? If you want to try this, pause the video now, and I'll come back in a second and give you the solution on this slide. Okay, here's the answer. Selection of the clubs, spades, hearts, and diamonds are independent events. For the clubs, there are 5 labeled as selected and 8 as unselected. From the labeling principle, we have 13 factorial, that's for the number of clubs, and then we have 8 unselected and 5 selected. So we have to multiply those factorials together, and that gives us the number of ways of selecting the 5 clubs. Then we go to the spades, so we get 13, and we mark the 6 of them as selected and 7 as unselected. Then for the hearts, we have 7 selected, 6 unselected, so we have this number. And then finally, the diamonds, we have 5 selected and 8 unselected. And so in order to get the total number of ways of getting 5 clubs, 6 spades, 7 hearts, and 8 diamonds, we need to multiply these 4 things together, which I've done here. And then there's some cancellation and so forth. And I got it down to this number here, which is quite big. It's roughly 4.877 trillion. All right, so let's continue. There's more examples. We have another poker-related problem. How many ways are there to deal a full house? 2 cards of the same value and 3 cards of another value. So I have an example here. Ace of spade, ace of diamond. So that would be the 2 cards of the same value, referring to the ace, not the spade or diamond here. And then 3 cards of another value, that would be 7. So for example, 7 hearts, 7 spades, 7 clubs. If you want to try it, pause the video. I'll come back in a second and give you the solution. So we'll break this into 2 parts. First, we'll figure out the number of ways of selecting the value, the card value for the 2 cards. So whether it be an ace, 2, 3, and so forth, but not the suit. And then the number of ways of selecting the value for the 3 card part of the full house. So that's what I have in the first paragraph here. S1, let S1 be the selected for the 2 card part. S2 be the selected for the 3 card part of a full house. So there's only going to be one value for this, right? It's going to be an ace or a 2 or a 3, and there's only one value for this, and then N is for not selected. So we have 3 factorial. That's the number of card values, ace, 2, 3 up to king. Then we have only one way of selecting S1, one way for S2, and then 11. These are the card values that are not selected. So there's 11 factorial. Okay, so then now we need to do is compute the number of 2 cards parts of the full house. So we have 2 cards selected and 2 that are not out of the given value. So for example, it was ace, we'd have to pick 2 of the suits to be in and 2 of the suits not to be in the full house. So we have 4 factorial divided by 2 factorial divided by 2 factorial. Then for the 3 card part, 3 of the cards out of the 4 of the suit are selected. So you have 4 factorial, 3 selected, 1 not selected out of that card value. And so you have to multiply this times this to get the solution, which is what I've done down here. And if you multiply all that out, you get 3,744. Okay, so that's the number of ways of getting a full house in poker from a standard 52 card deck. We have another card problem for the last problem in our lesson. How many ways are there to deal a regular straight? Again, we're talking about poker, not necessarily of the same suit. So you could have ace, 2, 3, 4, 5, for example, but they could be of different suits. Also, assume the ace can play 2 roles. It could either be the 1, or it could be the highest card in the highest rank, just above king. All right, so I'm going to give you the solution on this slide, but if you want to give it a try, pause now. Okay, so here's the solution, and I should probably mention one thing if you're not familiar with poker. The wraparound is not allowed, so you can't have queen, king, ace, 2, 3. That's not considered a straight in poker. So we first want to figure out what could be the first card. So given that we can't have this wraparound, there's only 10 selections. You have to have 4 cards above you, basically, for whatever card you pick. So there's only 10 possibilities. So we can mark one of the cards as being selected out of that 10 possibilities, and then the other 9 is not being selected. So using the labeling principle, we have 10 factorial, then 1 factorial times 9, or 10, or you could just reason to it being 10, right? There's just 10 possible choices. So once you pick a card like 6, then you have to pick what suit the 6 is, what suit the 7 is, what suit the 8, 9, and 10 are. So you have 4 choices for each value in the straight. So it's basically 4 times 4 times 4, 5 times. So you have 10 times 4 to the 5th, or 10,240. Okay, so that's it for this lesson. I have another lesson on the inclusion-exclusion principle, which can get kind of complicated, especially the proof of that. I did mention that in the very first lesson, but now I'll go into more detail in my next lesson. Then I have another lesson that just has a bunch of miscellaneous problems. Okay, so again, if you like this, please give it a thumbs up, and stay tuned for the next 2 lessons. I'll be releasing them roughly 1 week apart.